Swayam Prabha. Digital India. Educated India.
So we'll continue on. There it is. Okay. So we just stopped at what the reflection coefficients and the values approximate ranges are. So here, if you see the angle, things that is this when you see the angle of incidence, this is your reflected pressure. So the peak reflect coefficients are somewhere here, and clearly the pressures keep dropping. Now we come to perhaps there are two variations of this, but let us look at this particular chart or this particular graph. And we will be spending time in the tutorials also, again not today, but some other time. So this is, and relates also to the question that was asked. So if you see here, this is also from the UFC 3-340, and here if you see this is the positive phase, there is separate for negative phases as well, and then this is the parameters for spherical TNT. There is a separate curve for hemispherical TNT. So this is your building, and then if you have a surface, this is on the ground. So the terminology that is used, this is the this is hemispherical, and this would be spherical. So there is a similar curve. This is figure 2.7. Similarly, for the hemispherical, there is figure 2-15, and both are very similar in. Now several things to note here. If you see, this is the scaled distance. This is in terms of course feet per pound, and there could be, you can develop similar curves in SI systems also. So several things are there. The first one is your PR. So this is the reflected pressure, PR, and the scaled values go from 0, the number is taken out, I think it goes up to 10. Typical scaled values, now I haven't talked about, we've talked about the scaling. This is called mass scaling. So this is your R divided by W power 1/3 cube. This is also called the Hopkinson's cube root scaling. That's the terminology that is. There are other, we will look at that at some point. There are lots of other theories as well in terms of scaling, but this is one of the most popular ones. And here this is PR. The second one, if you see, this is PSO. So this is the incident, and then you have here these, there are 4 quantities, next 1, 2, 3, 4 quantities. These are in terms of scaled. So these are, if you see, this is the impulse, reflected impulse. This is the IS, I think this is the incident impulse. Let me see if I have, this is the scaled reflected impulse. Sorry, this is, I'm saying too many thises. Let me take these out. And when you open your 340, you'll see in a clear manner. So this is the scaled reflected impulse. So, and what's that? And this is your scaled. So some quantities are scaled. This is incident. So what you see is mainly, and then there are other quantities such as the arrival time, and then you have in this case, yeah, this is the solid line, this is the velocity that we talked about yesterday. You also have, so there are 7 such quantities most of the time, and this is the length, the blast wavelength. The blast wavelength is, they talk of a blast wavelength, it is nothing but the duration over which the blast is effective. So it is not quite the wavelength that you are looking for in a sine curve or any of the other periodic functions. So 7 parameters in figure 2.7 and figure 2.15 is the same thing for hemispherical bursts. So get familiar with these. You can look up the 340 and use these for some of, we will be using it for some of the problems that we have. On this side also they have the arrival time, somewhere the arrival times are here, and the duration. One of them is the arrival time and the other is the duration. You see there are 2 T's. If I blow it up, it is not going to be very clear, so you can see it in the UFC 340. In terms of scaled values, can convert them into SI values also. We consider the scaled distance anything less than 3.0, that is considered the cutoff point, to be near range. Near range is much harder to predict compared to far range. Far range, more uniform pressures, and Z greater than or equal to 3.0 is considered far range. What does that convert to? Do we
divide this by 2.5?
What's that?
Dividing this by 2.5.
2.5. So 3.0 by 2.5, that's how much? Roughly 1.2 or something like that. So this is 1.2 meters per kg. So anything less than that, anything greater than 1.2 meters per. So numbers to keep in mind, because it makes a big difference as you start visualizing what to apply and how to go about it. Any questions so far? Now, other effects that we have mentioned, if it is there, you should consider. One is, we've talked about confinement effects. These are not applicable for the above curves, are not applicable for confined structures. As you can clearly see, this is for, as they call it, explosion in free air at sea level. So you have confinement effects. Confinement, as you can see, it's a complex interaction of reflected and your pressures that are still emanating at the same time. So you tend to have magnified pressures, and UFC again has a whole range of curves. Whatever you want, it's like going to a candy store and pick what you want. It's got a wide variety of choices, different configurations, different openings, those considerations, closed versus open, confinements, all those curves are all different there. And the next thing to keep in mind is also ground shock. Other effects, ground shocks, especially when you have surface bursts or hemispherical bursts as they are called, it tends to do cause cratering. Some of the energy gets dissipated. Cratering effects can have foundation care. So you need to, there are ways to calculate how much cratering, the depth of cratering, the width of the cratering, sort of hemispherical or more of a cut section of a. So in that shape you can calculate some of the parameters, and there are equations. We used to actually spend a couple of lectures just on cratering alone. I don't think we are doing it in this particular class. And ground shock, some of you may be working on it, is significant for what type of structures? Underground, right? Buried structures. A lot of propagation is like seismic waves in some ways, but the durations are different. Anytime you're designing some of those, you have to go further into and defense applications. There are numerous underground structures, either for storage or primarily for storage of different types of things. These are generally neglected for overground, above ground facilities. And then the third thing, I'll try to present a little bit of it later on, is fragmentation. So fragmentation, especially when you have explosives in a casing. So as you can imagine, you have blast plus impact. Now impact, it degrades, it removes material. So when it removes material, you need to consider the section property changes and what it does to the response. So as you can see, it's a fairly complex, but the UFC 340 does address that to some extent. Let me see if I intended to take one more picture, but I don't know if I did. No, I don't think I did. Yeah, let me show you this also. So in case you're wondering, they do have, in the same way like you have figure 2.7, you have figure 2.8, where if you are calculating, we generally don't do this, but if you are calculating the negative phase shock wave parameters again for a spherical TNT, you have the same things, PSO, PR, scaled. This is the incident impulse, reflected impulse. These are the blast. So the scaled values, the pressures, these are not scaled. What I mean by not scaled is you don't have to multiply by the weight. In all these four quantities that you see, any quantity that you see where your result is in terms of the weight, then that is a scaled quantity. The others are not scaled. Then we are, again, remember the theme for today is uncertainties. So continuing with that, we'll go into element. The third one was element modeling. So we'll start with material parameters. For design, we simplify many things and use standardized curves. So the first one is, of course, you have strength parameters. strength adjustments or strength factors. And two of them that are commonly used are the strength increase factor. Both, especially concrete over time, does gain some strength, and you account for that. It's typically older structures that are subjected to these types of so you account for what are also known as SIFs. And then you also, even the same case with steel also, right? So when you have steel, you say it's 415 megapascals, that's just a standard. You test it, you might get definitely much more than that. So you have to account for those also. And just like in seismic you're evaluating the capacity of the structure at its limit. And then you also have what are known as dynamic increase factors. The dynamic increase factors are, or DIFs. This is, we were discussing over the break, the accounts for the effect of strain rate. So we know that all of you may be familiar with this, but if you see, let's say, the strength of concrete versus strain, if you have a normal loading, this is, let's say, normal loading, and if you're loading it at a much higher rate, you'll find an increase. So this is a higher rate loading. It might fail earlier, but definitely has a much higher, and this difference ratio, we account for it in terms of strength increase factors. So yeah, I think so maybe I wanted to show, oh, it fell behind. I wanted to show these ones. So, yeah, we'll keep it here itself. If you see the shape of the explosives, there are a variety of shapes that you have. It's not just a spherical one. And the shape of the explosive also makes a difference, but in our design we really are not accounting for it in any direct way. But coming down here, if you see, these are the different, let me see why. So I'm putting it here so that you can have it all in one document when you download it for reference for solving problems. So look at this a little bit in detail. If you look at concrete compressive strength, and it not only has for flexure, compression and direct shear, they have 3 different values. Masonry, then you have, if you see hot rolled steel, steel also is fairly high. Flexure and shear is 1.19, here it is 1.19. Shear, of course, is lower, here 1.1. And those are some of the other numbers for, this is irrespective of the units that you use. And what we were discussing during the break is it is dependent on strain rate, and it is really hard to measure at what you can see that different strain rates are going to have different ratios. So if you ask the question, what is the strain rate these are applicable for, it's really hard to answer that question. Now when we talk of strain rate, do you know what we are what do we mean by strain rate? Strain in the material, right? In the material itself. So yeah, keep that in mind. Quite often I mean, I've seen this, the word used and really being interpreted in a couple of different, in a variety of ways. But the response goes from static to a more dynamic. It's really hard to measure also. We were discussing about the difficulties of having sensors. These train rates can go anywhere between 100 per second to, it can even go to 1,000,000 per second. And the challenges that we were talking about was, how do you measure strain rates that go beyond 1,000,000 per second? You should have sensors that can respond, take at least 1,000,000 readings, right? Even that is not enough. It'll create noise. If you are going to have any accuracy in measuring strain rates at that, you need to have at least an order or two more than that. So, so that is knowing that we are using numbers, but also being aware of the fact that these are very challenging to get. And honestly, I feel sometimes people sit in a committee and based on their experience, they come up with a number that sounds good and agreeable to everybody, and it often goes in. I think just as an, can I take an aside moment? Do you know, have you heard of the stress reduction in extreme events, like in allowable stress design, right? What's a factor you've heard? So you can increase the allowable stress by, let's say, 4/3, right? 1.33. There's no real research behind that. It's just lots of engineers or whoever it was, a committee that sat in a meeting, had some lunch or whatever, and said, okay, 4/3 look, and that is used all over extensively, even into the new codes. It has, the 4/3 has been built into the load combinations, or so these numbers are somewhat in that. Keep in mind, keep the context in mind. If I look at, so that's for, and the other thing to also note is concrete strengths change as well with time. So you have what are known as strength increase factors. These are DIFs. So this is the right one for dynamic increase factors. Let me see if I have one for the strength increase factors. So if you, I thought I did, but I may not. But let me pull some of these, and you might be in for a good addition to something like this at the research at the end of this course. But if you see here, so these are dynamic increase factors. Okay, so this is dynamic increase factors for different types of steel. A36 steel, this is equivalent to your 250 megapascals, and your A992s are. So here you see this is the dynamic increase factor, and here the strain rates. Let me see if I may have a better. So this is starting from 0.001, and it only goes up to 100. So the strain rate is units of 1 per second. So this is 100 per second. And similar way, you have, I thought I had for concrete also. Let me see, this is for concrete, and okay, this is structural steel. So let me put this whole thing so that if we have problems, you can use these charts. So what you have here is for both so this is the first one is for concrete, and structural steel. And this is for reinforcements. No, A36 is structural steel too. Maybe they are the same. Grade 40. No, this is not structural steel. This is your reinforcement steel. So you have grade 60, grade 40s. The lower grade steels generally tend to have, seems to have, this is both for FU, and so again you see the strain rates, it's not super high, going up to 100, and you can have increases of up to 70% as the strain rate increases. Even here, if you see, you're going up to 70% in concrete also. This is from 17 megapascals to 48 megapascals, going from 1 all the way to 1.9. Yeah.
Are there any reasons behind this increased factor at high strain rates?
Yeah, I mean materially if you see, right, the material hasn't had time to develop, change their molecular structures. For me, I try to use some simple examples. Again, if you're compressing, you pull something really hard, right, it's so hard to pull it instantly, whereas I can take the same thing and slowly keep increasing it. That's sort of the strain rate effect. If I make a slow pull over time, I may be able to pull it apart. But if I want to pull it instantly, you can even feel, right? Try that. Pull it apart quickly, your muscles are working. Try that. Do this. Don't feel. So that's what is the. You can feel. You can feel the strain rate in your muscles, and then pull slowly. You'll hardly feel any strain in your muscles. Don't believe me. You won't do it.
Confinement play any role in?
Other considerations, this is a question that does keep coming up. One is damping. So structural damping, does it play any part? Now if you see structural, if it's an elastic behavior, you take a tuning fork, it's going to continuously keep going, right? At some point, because it's got damping, inherent material damping, this varieties of damping, we especially if you have done seismic, you would have a good idea about that. But from a material perspective itself, there is damping. For example, you have lightly cracked concrete. Okay. So lightly cracked concrete, the damping can be as much as 2% to 5%. Then if you have heavily cracked concrete, here you can have from 5% to 15%. And then if you have steel, bolted steel, these are just to give you some ideas. You can try I am presenting some of these numbers because you will have an opportunity to see if these make any difference in the response, or if you have welded steel, these are somewhere 1% to 3%. But in blast analysis, even for damping, you need time, because it is damping is nothing but energy dissipation, and in energy dissipation you need time for that energy to quickly to dissipate. In blast analysis, the time is very small, in milliseconds. So there are several things. We will talk about that perhaps tomorrow or day after. You will see that the response can be prolonged or short. We will see different curves. Response is dependent on the inherent structure properties and the duration of loading. So since those things are uncertain, again that is the theme for today, we neglect damping. Or in programs, if you use, you have to give some percent. So this is 2% is 0.02. If you want to give, you can say 0.002 or 0.001 something, so that the programs don't crash numerically. Give a very small percentage. And if you want to study the effect of damping in some of your tutorials, you are most welcome to do it, because the program would be capable of incorporating it, and I welcome you to try that. Then, so that is one. The second thing is post yield behavior. So we are going up to damage. So most materials we are considering to go beyond the yield point or the maximum point. As we all know that different materials have different behaviors. For example, if you take concrete and you are doing a P versus delta, so here you might have a variation that looks like this. But if you take steel, for example, and you have, it might be more, and that should be a straight line, could be more something like this. And past that, this is the softening zone. The softening region may or may not be accounted for, but when you look at the stiffness, so you are taking these are some guidelines for using a program called Nonlin that we are going to come up with. So you have up to yield, you have a certain K1, and here, for example, this is K1, this is the initial stiffness or the elastic stiffness, and the stiffness, as you can see, is in either newtons or kips per inch. And so that the programs don't crash, you can take some K2 value here. Steel, for example, if you consider 0.05 or 0.01 K1, again you can try to see, does it make a difference if I go between 0.01 and 0.1. It's up to you. There is no real guideline in incorporating some of that in the modeling. Whereas concrete, for example, you can perhaps think of it as 3 different stiffnesses leading up to. So we are linearizing the curve. This would be what is known as a resistance function. As we spoke about earlier, the resistance function can be either generated analytically, or you can do experiments in order to determine that. We are not considering some of these single degree of freedom system analysis don't quite consider the tension membrane effect. So, if you want to consider that, that comes from experiments, or you have to go really advanced, not the ones that we are using in this particular course, to consider the membrane effects. So, any questions again so far? Then the third thing is support conditions. Again, many of these are basic undergraduate. A lot of it is single degree of freedom systems are often developed based on assuming simply supported, and then other conditions are associated, are accounted for. So, different types of conditions, simply supported, and then you can have a cantilever type system, can have a fixed concrete. If you are modeling for concrete elements, for steel elements, if you are modeling a steel beam, for example, if you are modeling precast, pre-stressed, if you are doing a bridge type analysis, then you might go for simply supported conditions, whereas concrete, definitely you are going to use fixed or cantilever type arrangements or other type of simple conditions. So, you have to decide based on what you have as to what type of support conditions is ideal, because your response is going to depend on the support conditions. How are some of these accounted for in design? So, design loads, and I can speak with respect to the US codes. I am not too familiar with the Indian codes in this case. In the ASCE 7, so we have ASCE 7, the recent version is ASCE 7-22. That is our minimum standards for loading. So, they specify the following load combinations. So, it is 1.2 dead load. So, we have load combinations, and 1.2 dead load plus the blast load is, it's actually a recent addition, maybe I can't say how many years, but it's just in the past 5-10 years, or maybe I don't know if, I think ASCE 711 may have had that. I have to check on that, but it's been in the past couple of decades. So, blast load, because you're already including, it's just like even wind load. In our case, it has changed. Previously, wind load used to be 1.6 factors, but now since the wind speeds are factored already, all the graphs that we have for wind speeds, they are already factored. So, wind is also now, the combination has come down to 1, and then other combinations that you can include are 0.5 or snow. This is for roof, depending on which element you are designing for, or for uplift conditions you have 0.9 D or 1.2 D plus blast plus 0.2 W wind. So, there is some wind associated with blast loads. So, 0.2 W is considered. So, these are the load combinations as per ASCE 7-22. Elastic rebounds are usually neglected, as we have said before. It's the negative pressures are also lower. So, unless you confined yeah, maybe I should mention that. Elastic rebounds, or just rebounds in general, this is more critical in confined conditions. So, that is as far as some ideas into modeling. We looked at materials, we looked at dampening, we've accounted for stiffness, we've accounted for loading. So that leads us to modeling itself. And one of the most popular models is still the single degree of, we'll spend a little time on that, single degree of freedom or SDOF systems. And it's quite effective. Especially if you are looking at designing beams, slabs, even for that matter, things that are fairly, you can fit into one of these conditions. You can model them separately. Loads are different, so you can model them separately and you can come up with their responses. Now, what do we mean? I'm sure most of you know it. The thing to keep in mind is when we look at a degree of freedom, right? A degree of freedom in any structure is associated with, again, just some basics, your displacement degrees of freedom ux, uy and uz. So when you're looking at finite elements, when we talk of degrees of freedom, this is what comes to mind. At each node you have the same thing. Of course, here they are constrained, and then you also have your rotational degrees of freedom, theta x, theta y and theta z. So in general, a structure, even a simple structure like this, has 6 DOFs per node. But what we talk about here is not quite, this is the finite element representation, but now we are talking of a structural degree of freedom. So when you have a loading, whatever be the loading on the structure, here it's going to deflect in a certain manner. Let's take any type of loading. What we have to do is, this is the term for equivalencies. We convert it into one. You can also apply distributed loads in certain programs, and depending on how complex they are. And then the degree of freedom that we talk about is this deflection. So the structural deflection is the degree of freedom. And so when we take this structure and we say this is equivalent SDOF model, we are going to convert it into a spring system with the load applied, and we are looking at the delta that is the same as here, right? So the stiffness, again, that you use, it depends on several things. It depends on your boundary conditions. So the first thing is, that's where the boundary conditions was introduced, and it also depends on the type of loading. So all these, when you model them, you take this structure, apply a load, you take this structure, fix it, apply a load, or you take this structure, just some simple cases, apply a distributed load, or you take this structure and apply a distributed load. All of them will have a different stiffness. You're all familiar with this, right? Calculate from your deflection equation, and so these are analytical expressions of, these are coming from analytical expressions of your deflection equation. So, for example, here I think it is PL cubed over 48 EI, whereas this is, if you see, it is W5 WL power 4 by 384 EI, which is nothing but 5 by 384. WL is P, L cubed over EI. So, your elastic stiffness in this case is going to be 48 EI by L cubed. So, dependent on the load, this is K1 here, K3 is 384 EI by 5 L cubed. And for other types of loadings, other types of conditions, look up your tables or wherever you go to get stiffness values. So, this is important. I mentioned the difference here because you will be applying in some of your tutorials or some of the examples that I use. Any questions so far? Then the concept of this is modeling. So, this is the effect. There is a concept of equivalent mass. So, when you have a system, when we say an equivalent SDOF, we are basically representing this as F is equal to K delta, and what we are saying is, in this system you have a mass that is concentrated, you have a stiffness, and you have a force, let us say. So, here this assumes a concentrated mass, but then ours is a structures, they have distributed mass, and I will try to bring you some. So, therefore, you have to have an equivalent concentrated mass. So, you convert the distributed mass into an equivalent using a certain factor. So, that is another consideration that you have to keep in mind. Other considerations here are, we have talked of the resistance function. I think I have it here. Now, what are some ways of doing resistance functions? For example, if you are, and we will go through this. So, this is more not in terms of force versus applied deflection, but this is in terms of the resistance from the structural perspective. From the structure, what is the resistance, and then what can you use beyond that? So, how do you calculate Rn? I have already talked about the stiffness. If you have something like this, you can represent, we have seen how to calculate the stiffness. I have also shown how to use the mass, but we will also see this is usually from your design equations. So depending on the type of material that you have, your design equations from an analytical perspective you can calculate, and then the resistance functions. And it is, just for the sake of completeness, let me mention that at least the program that we are going to use, it's going to have resistance functions K1. It's going to have options of three different resistance functions. Of course, it does not account for post peak behavior. The post peak behavior is, from a design perspective, not important, but from a protection perspective it clearly is important, but you cannot predict it from these techniques. You have to do advanced techniques, and even at that it's at best predictive in nature. Other concepts that you have to keep in mind is some of the force parameters. The concept of FNR, which I call it FNR, this is nothing but, and it's fairly obvious to see it, it's the remaining strength. So the remaining strength is the total strength that you have minus the strength that is required to carry your dead loads, live loads, and the wind loads. That's what is available for blast resistance. And somebody was asking me with the applied loads itself. These are, you can take your pressure and multiply in whatever way. We convert most of it into some kind of a force. Even if you don't calculate moment resistance, as you will see, you will convert it to some kind of a force, and then that force is the equivalent applied loads. Again, this is a guideline. Often if your F naught by FNR is less than half, typically you will have an elastic response. But if you have F naught by FNR, is greater than 1 or much greater than 1, then, and you can, we will use this concept later for design purposes, but if you want a quick judgment of whether the structure is going to respond or is going to be, depending on the applied load, whether you need to consider blast response of this structure, then this is a good guideline. I should mention again that this is basically a guideline. There's a new concept. Actually, this was the concept that really fascinated me when I first started this, because yeah, you had a question.
Theoretical approach to find the remaining strength FNR.
Theoretical approach. How do you mean theoretical approach? This is, you can calculate Fn and you can calculate the capacity required for dead, live, and whatever load combination.
The remaining strength in the number,
In columns, right? Yeah. So I guess you, I don't know if I answer it. Let me answer it this way. Computation of the remaining strength after the application of a load is a very fertile area of research. I mean, people have worked on that. What is the remaining? How do you estimate it, or how do you calculate based on whatever section properties that remain? But again, here we are talking from a design perspective, and so this is a very simple form. But you're right; it is a fairly complex It could be depending on the type, whether it's a column or a beam. Is that what you're asking, or is this, am I missing something?
Yes, I want to know is there any way I know using an experiment or the numerical simulation we can find, but that is numerical simulation is also very expensive after applying glass flow. So there is a way to theoretically find the remaining capacity, because in the code they are giving guideline remaining capacity. So without knowing FNR, how we know this is erratic response or
No, I think this is the only way we will calculate for this course, at least, because these both are known quantities, so you can actually have a number. But I've seen a lot of papers where FRP, for example, they will use, and then they'll apply the regular loads and find the remaining strength, and then apply the new whatever mitigations, blast mitigation systems that they may use to, and then calculate the capacities. So in that context, I have seen experimental and theoretical calculations there, but yeah, not from a design perspective. So this is a concept, as I was mentioning, that I was never exposed to. When you have a regular structure, right, let's start with this. I have a simply supported beam, I apply load. If I want to calculate my deflection, what do you do? It's easy. It's not a hard question. If you know the answer, you just are not shy to say it. Gomati?
You want the expression for deflection?
Yeah, just give whatever expression you have.
W L square by 8
That's moment.
48
Yeah, 48 EI, right? So there is a direct expression for you to go. So you will say, for example, this is PL cubed by 48 EI, right? So there is the structure. There are two things associated with it, right? One is the structure geometry. The structure geometry comes into play in terms of I. So that's your structural from the geometry perspective. Then you have the material that comes in the form of I and L, I should say. This is material stiffness, that is your geometric stiffness. Combine them, you have your structural stiffness. Nowhere have we considered other material properties, other structural properties. If I take a structure like this, right, and I say this is an equivalent spring. Let's say I'm putting a mass out here, and let's say I hang the mass. Now this structure is going to have a natural frequency, right? Every structure has a natural frequency. Did that come into picture here? No. So you have the natural frequency. So this is the circular natural frequency, and then from here you can calculate the omega is, this is in radians per second, and then you can calculate the time period is 2 pi by omega, right? So this is your natural time period. So static loading is independent, or I should say the response is independent of the dynamic footprint or the dynamic properties of the structure. Even in seismic loading, this doesn't come into play much. But in extreme environments, when you start, you will see that now here is independent, and secondly, you also have the load duration has no effect on the response. Well, you might say if I keep the load for a long 5 years, it creeps, but that's creep. That's different. Again, that's a static behavior, right? But here the immediate response, so the deflection response in it is dependent on the duration of loading. So, this is Td and dependent on the natural time period. This is how one way to think of creative ways of mitigating is this particular concept. Now, we'll be looking more into these details, but again we are talking of blast basics today. So, all of this is again an introduction to ideas and concepts in this particular field. So, there are 3 different ratios. What is the ratio here? The ratio of to natural circular frequency, time period. If this, and there are other metrics also, this is considered, the load itself is different. It's considered an impulsive load. If it is between 0.1 less than Td over Tn to 1.0, this is considered to be a dynamic load. And if Td by Tn greater than 10, you can even go up to 10 here. Again, these numbers are not etched in stone. As you know, these are today's, a lot of it is still uncertainties. So, but roughly it's considered, this is considered quasi-static. Can you give me an example of the last one? Which UT machine. In natural phenomenon, buildings, any examples of quasi-static? Wind, right?
Wind load.
Yeah. So, wind, even if you see seismic, right, that goes into minutes. Your natural frequency, your time period is certainly not in minutes, even for buildings. So, this is, and the response, so what we see out on the left hand side is quasi-static, and these are some concepts that we will be exploring in the coming days. What is one good example between impulsive? Can you think of a sports application for an impulsive load versus maybe the other two?
Hitting a ball with bat.
Okay, that is impulse. What would be an equivalent quasi-static in that situation? Make up one. If you were to think of the quasi-static situation there, it's going to be keeping the ball on the face, right? And then trying to, have you played tennis? You play tennis, right? It comes, some people, Alcaraz and others, why do they hit so fast, right? Because the speed transmits, that's impulse that they are transmitting. triple jump, right? If I just jump, I can only jump so much. But if I come running, put that impulse, how long is the impulse? How many, is it seconds, that impulse? I come, hop, skip, jump, probably my milliseconds, right? So, and then you can propel yourself 18 feet, 20 feet, depending on the athlete or not. So, think of structural response in a very similar way, right? Am I making sense? So, these are just broad ideas that we will be talking more about, because when you calculate the differential equations, we will get a little bit into it. I think definitely want to introduce those flavors here. The calculations are different. The equations that you develop from the solutions of those differential equations are different, especially in our case. And again, we won't be getting into even the simplest form of a triangular load applied. When you solve it, it's a complex differential equation solution. So, without getting into it, we'll still use some differential equations over the next at least single degree of freedom systems we'll develop, and we'll see how the concepts are applicable. The response, right, here in the first static case, I apply a load, I know the peak. In this case, in the second case, the peak will be different, values will be different for impulsive load, the peak value if it is a dynamic load or if it is a quasi-static load. When the peak occurs is also going to be different. Make sense? So, this is a concept that I was certainly not aware of, but over time you realize what it is. We haven't done anything for a tutorial problem yet. Let me see if I can maybe skip a couple of it and cover those later, so that at least we'll have some things for the tutorial. We'll change plans. Okay, because we have 15 minutes left. So, there is a whole lot of, it's not quite an order, but that's okay. So, when you are in this field, you will see this being talked about. We have seen that this is one scaling law. This is called the cube root scaling. And so, cube root scaling is your R divided by W power 1 by 3. What does this mean? We have seen earlier that the pressure values are dependent on Z. So, if you consider two scenarios, let us say this is your structure and you have an explosive. In this case, this is R, say R is 100 feet and this is 1000 pounds. Same thing in this case, but now this is 27 pounds at, so we'll keep this as R1. The pressure on both are the same, depending. So, the Z in this particular case is R, and I have chosen numbers so that it is easy to calculate. So, R by W power 1 by 3 is 100 divided by, so basically this is Z is so many feet per Now, here if the Z is the same, the pressures are going to be the same. That graph we showed, right? Of the Z value you can calculate. So, for same Z, you have identical pressures. So, question is, what should be the standoff? So, 30 feet, right? So, in this case it is now 10 is nothing but R divided by 27. So, this is at, so this is more than a number. What you have to keep in mind, look at this, 27 pounds at, I am sorry, 1000 pounds. So, basically what this cube root scaling tells us is 1000 pounds at 100 feet is the same as just a hand bomb 27 pounds at 30 feet. So, helps us in designing your whatever surroundings, how far to keep people away. That is why you see all those protections. It is a very quick way to determine some simple parameters in the overall scheme. The impulse, if you look at it, also scales. I1 in this case divided by cube root of W1, and this is I2 divided by cube root of W2. So, if you see in this case 0.3 I1, because this is by 1000, is I2. So, peak pressure, what you see here is peak pressure, note the difference. Peak pressure is, it's a simple example, but there is a story behind this. Each one of these have something to focus on from a concept, from the response perspective. The peak pressure is the same for both cases, but impulse is not. And remember, there are three variables. In blast, primarily there are three variables in terms of loading, pressure, time, and impulse. Impulse, as you know, is the area under the pressure time curve. So, either you consider P versus T for loading, or you can also look at P versus I. That is where some of the pressure impulse, we talk about it, the pressure impulse diagrams comes into play. What it says is you can have, for example, a structure with different pressures, let me put it this way, for different combinations of pressure and impulse, you can have the same response in the structure. You can change the pressure, increase the pressure, decrease the impulse, response is the same. Decrease the pressure, increase the impulse, response is the same. Some of these concepts again are not quite applicable to static loading that we normally use. So, these are some concepts we will be introducing, as we go. Yes.
This scaling law is applicable in for air blast only or soil, underground soil? Just yes or no?
There are different scaling laws, but the scaling law I am presenting cube root scaling. I'll give some ideas on what the scale, some different types of scaling laws in another class, but this is for air, applicable for air bursts. I like the way he said yes or no. My choices were very limited. So there is also the response limits. Well, I don't have the graphs, but we'll talk of the response limits. So I think in the remainder time I have, let me see if I have that. That might be the best thing to do now. Yeah, okay, this is good. So let's say, and we've talked about this, but let's look at some numbers, response limits. And if you can't see some of these well, let me know. I'll try to upload your pictures. Oh, what happened? I didn't touch anything. I hope it got saved. Oh, it came back. Okay, let me save that. It came back.
No, but screen.
Yeah, it just went blank, but I think it is. I can feel it heating up. I don't know if that's an issue.
Next page.
Yeah, that's what then it'll give me more. Yeah, I think this is perfect for the time we have. I know you must all be hungry too. So if you see, this is, I don't know if it is clear enough, but I'll try to. Several things to observe here. This is limits on, remember mu, we call this the ductility ratio, and theta, this is the support rotation. So if you look at again, this is the damage level. And if we look at, say this is RC, reinforced concrete. So superficial, the first, if you can't see, the first column is mu and theta, so on. Mu max, I should say, and theta max. So for concrete, if you see, only at the superficial level, damage you have mu, right, which is 1 basically. But then you start getting into moderate heavy, they don't specify in terms of theta anymore, 2 degrees, and this is singly reinforced beam, doubly reinforced beam, so on and so forth, with shear reinforcement, without shear. So here it varies from 2 to 10 degrees for support rotation. In some cases you have both. Pre-stressed concrete, again you have mu and theta. Same thing here. So this is PS concrete, and in pre-stressed concrete, choose, what we do here is we apply the worst, apply both. As you can see, the choice is basically apply both, limits, and choose. the worst. Lowest load or the load, the least load that causes either one of them. So, and here if you see, this is for pre-stressed concrete, it goes 2 degrees. Numbers are again what we are all about. Masonry, it goes up to 15. This is masonry, reinforced especially. Now, if you look at structural steel, here you can see there are both, goes up to from 20 degrees max for hazardous, and least of course this is specified only you have only your ductility ratio here, but it goes from 3 degrees to 20 degrees. Then I think it's heating up. No? Oh, it came back. Anyway, we are almost done. I just want to present one more. It's it's not shutting down, that's for sure. It's just that the screen goes blank. And this one, if you see, this is for flexure. Clearly, ductility and support rotation, this is for flexure. So, this is beams basically. And the last thing we'll do before lunch is one more. Is if you're working with columns, this is for compression elements. Basically, you're looking at, and in columns you see the same thing. RC is only 2 degrees, and again here you're looking for theta max except superficial, and you have FRP also, some composites, structural steel, hot rolled structural steel, it's a little bit higher at 3 degrees. So, I think we'll stop with this.
Yeah. So for the tutorials
We have some questions associated with the familiarity of the code.